Welcome all faculty members and participants who have joined this FDP from various institutions. Now I request Dr. S. Yuvraj to deliver welcome address over the speaker.
Good afternoon to all the respected dignitaries, faculty members, researchers, and dear participants. It is my great pleasure to extend a warm and cordial welcome to everyone present for today's session. On behalf of the organizing committee, I feel privileged to welcome our distinguished resource person, Dr. Navin Raj sir. Dr. Navin Raj sir is currently serving as an assistant professor in the Department of Mechanical Engineering at NIT Puducherry. He completed his PhD and MS in Mechanical Engineering from IIT Madras, where his doctoral research focused on multi-objective optimization of low-altitude seat ejection with novel pain injury parameters, reflecting strong expertise in optimization and structural dynamics. Following his doctoral studies, Dr. Navin Raj gained valuable research and industry-oriented expertise as a senior project officer at IIT Madras, where he worked on advanced machine learning and data science projects. His work involved developing machine learning and deep learning models for time series forecasting and causal analysis, along with the guiding interdisciplinary research involving physics informed neural networks, Bayesian optimization, and data analytics. Dr. Navin Raj sir research interests span several cutting-edge areas including scientific machine learning, optimization algorithms, structural dynamics, AI and ML for mechanical systems, physics-informed learning, and human vibration response. His work aims to integrate advanced computational intelligence with traditional mechanical engineering problems to develop innovative and intelligent engineering solutions. He has contributed significantly to the research community through publication in reputed international journals and conferences. His work includes research on physics-informed neural networks for nonlinear vibrating systems, digital twins, polymer gear failure prediction, and structural systems modeling, published in leading platforms such as knowledge-based systems and engineering failure analysis. We are indeed honored to have such a dynamic researcher and academician with us today. His interdisciplinary expertise in machine learning, optimization, and mechanical systems will undoubtedly provide valuable insights and inspire all the participants. On behalf of the organizing team, I extend a heartily welcome to Dr. Navin Raj sir and sincerely thank him for accepting our invitation and sharing his valuable time and knowledge with us. We look forward to a highly informative and gaining session. Thank you.
Thank you, sir. Now I invite Dr. R. Navin Raj to deliver the technical session. Sir, the session is yours.
Thank you, Dr. Yuvraj and Dr. Shivkumar for the introduction. So I'll just share my.
Thank you, sir.
My screen visible?
Yes, sir. Screen is visible, sir.
Yes. Okay. Okay. Thank you for inviting me over to have a talk in this optimization FDP course. So what I thought was I will touch upon basics of probabilistic optimization with scarce data. Basically, this is using two important processes such as Bayesian optimization and Gaussian process regression. So this is one of the problems that we usually face in mechanical engineering. So because we don't have the flexibility to conduct more and more experiments, because most of our experiments are very costly, either in terms of computational power or time or monetary needs. So most of us here are constrained with these conditions, and then we have to work with scarce data but producing meaningful results, right? So that is why how we can use statistical techniques from mathematics and machine learning so to improve our judgment and kind of get a reasonable results from the scarce data that we have. So I would like to touch upon these basics in this talk. So the talk introduces about the foundation of why scarce data, what is optimization with scarce data, what is probability, what is Bayesian theorem, what is Gaussian process regression, and what is Bayesian optimization do. And I'll also give you some hands-on, show you some hands-on examples and plottings of how these things work and stuff like that. So as discussed, many real-world problems are expensive function evaluations, and most of another issue that we face is we don't have gradient information available. As we all know, most of our optimization algorithms that we use are predominantly gradient based, or we go for something called as heuristic. So the trade-off is whether you have the gradient information or you don't have the gradient information. In cases where you don't have the gradient information, we have to do lots of function evaluations, and each function evaluation is going to be very costly. But as I told, in our cases, like for example the wind tunnel experiments, which is going to be very costly even in single case of run, or drug dose optimization, or where we have to wait for sometimes to see outputs, or CFD simulations, like even for one evaluation it is going to take 12 hours, and then if we made an error we have to spend another 12 hours. Material property optimization, where it is the materials are going to be very costly. So these are the common examples that we usually face in mechanical engineering. So that is why we are going on to usually these are the four optimization techniques broadly classified. Like it's not very good, but broadly classified, Bayesian optimization requires 20 function evaluations. Let us assume that if it requires 20 function evaluation, gradient based will require 100 function evaluations, and random search will require 1000 evaluations, grid search will require 10,000 evaluations. But the idea is we can increase the efficiency of Bayesian optimization is going to be reduced, but the uncertainty bounds that are going to come along with the Bayesian optimization kind of tackles this. So it gives you an information of where exactly the design parameters can be taken from and what uncertainty that you can expect out of it. So we are actually trading off between accuracy and uncertainty quantification, but making an informed guess or informed solution with the data that we have. Right, so this is how we can visualize traditional versus Bayesian or a smart optimization technique. So in grid-based search or brute force search, we usually split the column. Even in Taguchi methods or different methods, we kind of fix our computing points, and then based on those computing points, we evaluate the function, and based on the function values, we kind of get to the optimum function. But in Bayesian optimization, what we do is we estimate the points where we have to evaluate only after the previous function evaluation. So basically, we will be trying to fit functions, and then is trying to surrogate the model, surrogate the physical phenomena that is there behind, and then based on the surrogate model is going to give us two information. One is the function value and the uncertainty that is associated with it. So based on these two, how we can go ahead and sample at a new point. For example, if we had taken 5 points that are in the middle, where to sample in the next. Usually by grid search, we usually split it like this. By where to sample next will be given from the formulas or statistical information that can be stored. So this allows us to intelligently work over the topology or intelligently work over the space that is given to us and try to find out the optimization optimal function values, right? So before going on to what exactly is Gaussian process regression and what is Bayesian optimization, a small intro to the basics. So as we all know, this is a Gaussian function. So this Gaussian function is given by p of x greater than or equal to 0, and so these are the properties. So integration of this p of x is going to be equal to 1, and mean is equal to expected variation, which is equal to x into p of x, and standard deviation is expectation of x minus mu the whole square. So basically what these two numbers say is, if you are going to randomly sample from this probability distribution, so it is the reverse way. So if you are going to once you construct a probability distribution, if you are randomly sampling, the most of the numbers will fall near the mu line, and very least numbers will go away from the mu line. So that depends upon your sigma parameter, which is the standard deviation. So how your spread is going to be is dependent upon the mu and the standard deviation parameters. For example, the orange curve here, most of the values are going to be near your mu, near your mean, which means that there is very less error. So basically, as and when your model prediction is near the expected value or the expected mu. So this is where we take a turn from deterministic prediction and probabilistic prediction. In deterministic prediction, we only predict one value, but in probabilistic prediction, we consider that value to be our expected prediction, and then we fit a variance around it. So this expected variation, this expected value, how close this is going to be, that measures the amount of error we can have. So for example, sigma square is equal to, for the green curve over here, even if you sample multiple times, the sample values are going to be spread throughout. So this is going to give us very large error, but from the mean. So whenever you are sampling from the orange curve, all the data points that you have sampled are going to lie nearer to the mean, and most of the values are, I mean, very few values are going to go away from the mean. So this can be considered as a case of having lower error. So ideally, we would like to have more and more functions with orange kind of curve. But the point is, we not, as we have more data, our uncertainty functions or the probabilistic function converges to these kind of what to say, a very narrow band probabilistic distribution functions. But when we have lesser data, obviously we'll be working with this green kind of functions. So that is what we are trying to see how it is going to work. Another important thing that I would want you to tell is joint or conditional probability distribution. So joint distribution is where you have two variables. So the previous one had only one variable, that is x, and y-axis was probability of x. What is the probability that x is going to happen? So here now, as we go, we might have multiple model predictions. So in all our engineering examples, we have multiple variables, all those things associated. So everything can be fit in the form of Gaussian. So just consider this Gaussian. I have just drawn a 2D representation, but if you want to imagine this, just imagine this as an inverted bell shape of Gaussian. So just this is exactly going to be an inverted bell shape. So P of x comma y is going to be equal to it will be a 2D surface or a 3D plot with an inverted bell shape, and these will be the projections to the x and y axis. So there is the projections to x and y axis can be considered as different marginalization. So if you are going to integrate along y, you are going to get one marginalization, which will give you P of x. If you are going to integrate with respect to x, you will get a marginalization with respect to y. So, and conditional probability, which we will see shortly when we are seeing Bayesian rule, right? So when coming to Bayesian rule, so before seeing this, I would like to go on and explain with the small working example. Let us just consider Bayesian theorem. What Bayesian theorem says is, as and when you have data, our model parameters are going to be W. So basically, whatever model that we are trying to build, so all these models are going to have parameters, right? So these parameters are what we would like to estimate. So what people thought was, instead of finding uncertainty in this data, if we can find uncertainty in the parameters itself. So what are all the parameters that can fit this data well? Because all these parameters can be optimized to different extent. So if you increase one parameter value and if you decrease another parameter value, we may still be able to get a good result, right? So what is written here is probability of the weights given the data will be equal to probability of the data given the weights multiplied by probability of the weights divided by some posterior term. We'll see what it is, right? So probability of D is the observed data and probability of W will be the weights, right? So here for this example, what I'm going to try to explain is, let us assume that we are going on a spaceship and then we are given a task of estimating the percentage of water in some planet. So we are actually sent to space. Just assume we want to estimate the percentage of water in a planet. If it is Earth, we know that it is covered by 70%, which is actually calculated by using multiple experiments, satellite images and everything. But as we go to a new planet, we don't know what it is going to be. Let us assume that you don't have photographic images and all that. All you can do is you can just put a probe down, and whether it touches water or not, water or land, only that you can imagine. Just consider you are going to do experiments, just putting a probe down, whether it touches water or it touches land. But again, with least number of experiments, we would like to estimate the total probability distribution. So this is the task that is given to us. So let us assume that probability of water given just relate this water to the weights that I discussed earlier and data to the real life data that we see. So the probability of weights, probability of water given data will be equal to probability of data given water multiplied by probability of water, so given by the normalization term. So probability of water, P of W here is called as some prior probability of water or prior distribution. So these are the new concepts that might be introduced differently. So prior probability is nothing but what is our intuitional guess or based on historical data what we have seen. So prior is something that we are imagining that the water is going to be. So usually it is better to imagine uniform distribution. So uniform distribution means the water percentage can vary from 0 to 100. So each percentage of water is given uniform distribution. But if for some reason we are having an intuition that it is always going to be greater than 50%, we can model that also. We will see how to model that. So posterior of water is probability. This is read as probability of water given the data. So after you have done some 10 experiments, let us assume that after you have done some 10 experiments, so let us assume you have got 7 water and 3 land. It is not going to be that 70% of since you have got 7 water, the whole planet is covered with 70% of water. But you have done only 10 experiments. With the 10 experiments, you have measured 70. But based on probability sense, if we are able to fit another probability density function to get a different approximation, that would be better. That would enable us to see it as a different scenario, right? So that is what we will see now. So basically, as I told you, I am setting my prior probability equal to 1. So uniform prior is taken for all the points between 0 and 1, where 0 represents 0% of water and 1 represents 1% of water. Okay. So let us assume that by random chance I have got this. So if you want, I can just type randomly multiple measurements. So just consider this to be the measurements that you are making, or when your probe is going down and touching the water. For example, touching the surface of the alien planet. For example, in the first one you are getting water, second one land, water, water, land. So this is a totally random sequence, and you can delete or enter whatever values you want. I'll share the code, you can work with this. So basically I'm counting the number of waters and counting the total thing. So if I'm running this, probability of water, first probability of water is going to be depending upon, so the first probability of water is going to be depending upon the number of thing that is seen. But if you are going to fit a binomial curve to it, so basically what this says is, I have seen 52% of water. Based on the measurements, I have seen 52% of water. So there is a high likely chance that there is 52% of water. But depending upon the variance in the data, so from this data that we have observed, we have calculated the mean, that is 52%. But depending upon the variance that exists in this data, we can actually fit a variance to this curve by using, here we have used binomial distribution because there is only 2 classes. So by seeing this variance in the data, we have put this curve. So I have just used binomial probability mass function here. So it is an inbuilt library used in Python. So this is going to give us what might be the probability percentage, what can be the likelihood of these percentage of water. For example, since we have already seen multiple water and land values, percentage of water for 0 and percentage of water for 1 is going to be very less, very minimal. So because we have seen enough number of W and L to negate it. So basically see this as a probability distribution function for percentage of water that we have estimated. So the main thing that we have done here is, instead of actually calculating our mean alone from the data, we have also calculated the variance from the data and used it for some meaningful measurement. So as you can see here, there is a peak around 0.52, but even other values of water are given some variance because these chances might also exist. So as you collect more data, the data might converge to one particular mean. So what we start off with the like our green function here. So as we have less data, what we start off with the green function here, as we get more and more data, it is going to converge to something like an orange data. That is what I was trying to tell earlier. So this is how you can actually use probability to use when you are having very less data points. So this is only for measuring some simple phenomena, but for doing an optimization, we will do some other procedures also like fitting and surrogate and finding the variance of that surrogate as well. So the main takeaway from this is not don't extract mean alone, but also try to extract variance always. So this variance is going to give you much more information. You can fit multiple probability functions and then you can really make statistically informed decisions, right? So now let us assume, since we had, so as I told earlier, so this is the probability curve that we have estimated from the data alone. So your Bayesian term does something like this, which is nothing but multiplication of your likelihood into prior divided by normalizing term. So the normalization is only to keep the probability score between 0 and 1. So what Bayesian algorithm does is, or Bayesian theorem does is, it tries to weigh in what we have seen and what we already know. So as I told you earlier, prior probability of water is from the information that I already know. For example, let us assume there is another team that has conducted some experiments already and they have given you some information. So, or we are having some strong belief that the probability of water here is going to be more than 50%. So this is what is called as a Bayesian term. Let us see how this Bayesian term is actually going to have an influence on this. So here you can see, initially we assume the uniform Bayesian term. So there is going to be not much change. So whatever we see in the data is going to be reflected back, and we are dividing by unstandard coefficient or sum. So basically we are summing all the probabilities and dividing by it so that all the values go between 0 and 1, right? So, but as I told earlier, let us assume that due to some prior knowledge of the probability of water, let us assume we have more than 50%. That is, I'm very sure that at least 50% of the planet is water and at least 50% of the planet is land. So what I'm trying to do, percentage of water less than 50%, I'm mapping it to 0, and percentage of water above 50%, I'm mapping it to 1. Previously we had a different case, right? So previously we had all to be 1. So in this case, supposing if you are doing a multiplication, so this is what you are going to get. So as and when your data is getting, the prior and the probability, so both these intuitions play together, and then this is how your intuition is going to work. But the catch is, the beauty of Bayesian algorithm is, supposing if we take number of water count to be 2, which is very counterintuitive, and out of the 10,000 samples, water count is equal to 2, which is very counterintuitive to the prior information, right? The prior information, we assumed that 50% or more of the planet is going to be equal to water. But now we assumed that, but the real life data is telling us I have 10,000 times probed the planet and I have got only 2, which is statistically very impossible that 50% of the water is going to be a planet. So while doing the same process again, so this will be, I have just copy pasted all piece of code. So this will be our probability distribution function. So the main core here is, the main cache here is, as your data set size gets increased, the effect of prior diminishes. So even though you start with a very bad assumption of having more than 50% of water, but your experiments gave you only 2 out of 10,000. So this Bayesian beautifully works out to say that when to trust prior term and when to trust your data. So this is how you can create multiple probability distribution functions, right? So this is one such example, and there are a few more examples that I have added here, but we'll move on to more optimization perspective. I'll share you this thing. You can just upload it to Google Colab and run it off. So that would be a good exercise, and try to get a hands-on on this probabilistic and all that stuff. Right? So now we'll move back to our probabilistic-based optimization techniques. So as I told you, these are our likelihood term, prior term. The evidence is nothing but the sum of the multiplication factors. So evidence is where your overpowering actually happens. So basically, prior data, what we believe before seeing the data, and likelihood, how well theta explains the data. Theta is nothing but the parameters. So as I told you, the parameters of the model here, since we are just taking weights, here we are just taking water, we didn't have any parameters. But usually in machine learning or any other surrogate models, we will have a model which will have some parameters. So which is going to be theta. So how well theta or the model explains the data. So posterior is going to be the updated belief after seeing the data, which is obtained by multiplying the likelihood and the prior, and then taking a and then normalizing it. You can just take that as a normalizing term, but in most often times calculating this normalization is going to be very difficult because it is computationally intensive. So for the example that we took, it is a 1D example, so it was easier, but the normalization term is the key term that we might want to spend some time on. Okay, so as I told you here, we usually start with the prior belief, which is the green curve. After 4 observations, our data will try to shift towards the mean, whatever mean it is, and after 12 observations or more number of observations, this is a very small example that I took, so that is why we are using this. So after more number of observations, the data, the posterior actually sharpens, and we get a good information about what actually is existing. The prior information gets overpowered by the data, because what we see as data is the true information. We should always believe the data that we see, even though it is behind our prior intuitions. So this is one way to make sure we are ethically and morally right also. Right? And this is the explanation for a multivariate Gaussian, how multivariate formula for multivariate Gaussian, how multivariate Gaussian can look like. I'll just skip these things and then try to move to multivariate Gaussian. So in Gaussian, what happens is since you have two distribution, multivariate Gaussian is actually multiple variable Gaussian estimations. So since you are having multiple variables, you are going to have multiple mu's and multiple sigmas. So usually these mu's are represented in the form of a vector, mu1 and mu2, and all the sigmas are represented in the form of a covariance matrix, sigma 11, sigma 12. So if you are having 3 variables, you can have more number of variables. So each data that we try to get is going to be one of this form. So every data is going to have x1, is going to be considered as x1 or x2 or x3. So as and when you are collecting more number of data, your mean and your variance is going to be shifted. Like your number of data points is going to increase. And then there is this key result which has some analytical derivations, where when you are having a new data point, depending upon the measure of how x2 is different from mu, once you have your normal distribution and then you have x1 and x2, you can actually reinforce, or you can change the shape, or you can recalculate this Gaussian distribution by using these formulas. So this formula actually elegantly tries to tell us how to fit a function when given the data points. So basically you can think of Gaussian process as similar to a parameterless regression. So here what we do is we try to calculate the mean of the function. M of x is going to be given as expectation of the output value, and then there is the covariance kernel function actually determines how far or how equidistant your points are. And for example, if 2 points are near and they vary very slightly, which means that their distance is proportional to their function variance. So this distance and the functional variance is these two, how they interact is going to be captured by this kernel function. So there are multiple kernel functions that are available. For example, we can just take our L2 norm, just our Euclidean distance as our kernel function, and then we can try to satisfy or we can try to fit a Gaussian process regression. So this GP here, what it does is it does the same thing exactly here. So as and when you see new data, it calculates the new mean and the new covariance function depending upon whatever kernel that you are choosing. Okay. So, and as I told you earlier, so your all fitting of this function is going to start from a prior. So you always start with the known sigma, that is going to be sigma 1 2 or sigma 2 2. So and then try to fit it, right? So usually it is better to sample from a uniform function. So whenever you don't know anything about the data, so you usually all these functions, so within a plus or minus 2 standard deviation example, before seeing data, all these functions are equally likely. So basically, if you are going to, how you can evaluate this is, you can have multiple realization along the x-axis and then evaluate the function value. So since all these are in the form of probabilities, you will have different function values for different time. So this is going to be one realization. Every line here is going to be one realization. So the mean of all these realizations will give you the actual result that we are expecting. So that is how we should understand this. And as I told you, x minus this is one squared exponential or radial basis function. So this is very similar to the Euclidean norm that we take, and where L being the the frequency parameter or how smooth your function is going to vary. So this is one of the commonly used kernel function. So there are multiple kernel functions which should be actually tuned and checked for. But most engineering or mechanical engineering problems, the squared exponential kernel will be of very good use, because most of our functions are not high frequency varying function. They are mostly low frequency varying. For example, even if you fit a second order or a fourth order polynomial, which we mostly don't often cross, at those times we can easily fit with these things, and by controlling the factor L, how rapidly these variations happen, we can check. So yes, so these are the so if your variations are varying very slowly, you can have a higher L value. If your variations are moving very fast, you can have a lower L value. So for example, if you are trying to fit if you are trying to fit a Gaussian over an image, then each pixel is going to change multiply, because each neighboring pixel is going to have multiple different color values and all that stuff. So in those cases, you can think of it as high frequency varying. But most often times, the response function that we see might not be like this, because we will try to transform all our features into a different space. Yeah, so this is exactly the formula that we saw earlier, and but the beauty of this is we don't have to do all these things now, because most of the codes are available, and all libraries now gives you what is Gaussian process regression and how to use Gaussian process regression and what is Bayesian optimization. All we have to understand this is from a functional perspective. We don't want to implement all these things, because all this implementation has been already done and is given to you in the form of packages. So if you can understand what actually is happening and then try to implement with our algorithms or with our data that we have, this is going to be of very much useful, right? So this is how actually a Gaussian process regression is going to look like. So if let us assume that we only have these many orange data, so we not only fit a regression curve, we also get this uncertainty band from the data that is from the covariance matrix that is being created. So all this data is going to be multiplied with the kernel functions to calculate your covariance matrix, and the mean of all these data is going to give you the mean function. So this is how we usually create the Gaussian process regression, and Gaussian process regression is actually used to do our Bayesian optimization. So what Bayesian optimization does is it fits a Gaussian process regression, and then it sees the places where you have higher variance and lower variance and a very low mean if you're going to do a minimization problem. So basically we do our minimization or maximization on this fitted function, but with an additional knowledge of how my variance is. So for example, my two global minima can occur here, because this is again within the functional range. So as and when we more collect the data, we might see the local minima or global minima coming down, because from this graph we see that this is the most lowest point, but the probability density function or the probability bands or the uncertainty bands kind of say that this is going to be your lower minima. So in these cases, what we have to do, we have to kind of sample in this place also. We might want to rerun an experiment at this place to understand how my data is going to look at this. So we would want to have some functions to quantify where to sample next, or where to conduct our experiment next. So that is what we will see shortly. So step by step intuition. First, start with the prior, that is going to be uniform prior. So mean 0 and some standard deviation k, which is going to be a uniform prior. Observe data points, compute the kernel matrix, condition the data or do the matrix algebra to get your covariance matrix, all the fits, get a posterior mean and get a posterior variance. So do all these steps to find out these functions. The posterior mean and posterior variance is going to give you or plot these functions directly. So once you get this, basically you will be doing train a surrogate model on the data, maximize the acquisition function. Acquisition function is what we will see shortly, and run an expensive test on the x next. So basically this x next will be determined based on the acquisition function. So this x next should be on the data where we see, on the place where we see more variance. So basically, so just by applying standard deviation, we can see where the standard deviation or the variance is going to be more, and in that place we would like to conduct an experiment to tighten the band in this particular place. So if we can tighten the band in this place, if we have enough time or enough resources to move to a next experiment, we can again do this experiment again to reduce the bands overall till we are enough or till we are satisfied with the amount of data that we have and the result that we have and the uncertainty that is associated with this. So this is how we usually make an informed decision based on these things. Okay. So acquisition function actually tells you where to sample next. So there are three ways to check. There are three usually common choices that is used. One is expected improvement, other one is probability of improvement, and the other one is upper confidence mode. So these are the three functions that is usually used to make a decision where to sample next or where to conduct our experiment next. That is, assume you have conducted 10 experiments with some 10 different parameters and you have an objective function value. So after fitting the data, where to conduct your 11 will be decided based on this. So like we saw in this graph. So where to conduct our next experiment. Next experiment, if we can conduct in this region, we are beneficial. So that is what we would like to estimate. So just to give you an idea of what I just told earlier. So these are the regions where we can exploit. Where we can exploit is where you have a tighter uncertainty bounds. So exploit means you can make informed decisions on the places where you have tighter uncertainty bounds and you have a very well defined mean. But explorations are the regions where you have a very high bandwidth of uncertainty associated. So in those regions you have to explore more, which means explore means we have to conduct more experiments. So for this we will be using two conditions, expected improvements and upper bound. So which will actually look like something like this. The expected improvement plot is going to look something like this. So again, all three functions is going to measure only the variance, but like we have different error functions, mean squared error, mean absolute error. These are all different functions. So you can just try it with multiple things and then do the next graph. So as I told earlier, wherever the variance is high or wherever there is a chance of improvement or where there can be my optimum lying, in those places I will go and sample next. So this is the expected improvement graph, which clearly shows that I should sample next. Even by our intuition, we knew that since there is a minima here based on the function and the variance is high here, so I can have my graph can further go down. Based on this realization of the data, I have this graph. But once I sample here, my graph can further go down. That is why I want to sample here, which is exactly what my expected improvement graph also tells me. So, and upper bound confidence is nothing but you see the upper bounds, you try to fit a absolute value for my upper bound and then see where the graphs are high. Depending upon these two, mu plus k into sigma x. So upper bound confidence will take mu plus k into sigma x, which is also taken in expected improvement in a different form. So then if you are taking mu plus k to sigma x, again it tells you, in this case also it will tell you to sample at this position only. Right? So when to use Bayesian optimization, this is very important. So whenever you are having a continuous search space, so if my search space is discrete, we might have problems fitting this Bayesian optimization or Gaussian process regression. So only when your search space is nothing but the parameter values. If your parameter values are continuous, you can always go for a Bayesian distribution and moderate dimensionality or low dimensionality. So more than 20 dimensions, more than 20 features. So for example, in the above graphs we had only x, only one feature and one output. But more than, so like that we can have multiple parameters. So if you're having more than 20 parameters, my Bayesian optimization is going to struggle. Why it is going to struggle is all the matrix operations which we did earlier. There is going to be a lot of inverse that has to be calculated, which is going to take a lot of time. So this itself is going to be a computationally expensive process. So expensive function evaluation. This is the very most important thing. Whenever your function evaluation is very expensive, it is always good to go for a Bayesian optimization, because it takes the data, also the variance in the data, tries to tell you informed value where you to sample again. So it kind of moves in the search space in such a way that we cover the search space fully with the probability and the variance data. So yeah, this is and very high where this is not ideal, very high dimensional data. When your function evaluations are cheap, you can always go ahead and do your gradient descent or heuristic algorithms such as genetic algorithm or particle swarm algorithm. Discrete or combinatorial spaces, again, it is not going to be very ideal. Highly parallelizable evaluations. If you're going, if the evaluations are parallelizable, then again your gradient descent might work better because of the libraries that we are having today. And if your function is going to need multiple function evaluations, again this is going to be very problematic, right? So usually in one place where we commonly see is Bayesian optimization is used for hyperparameter tuning of neural networks. So instead of doing a grid space, usually hyperparameter tuning, all your libraries try to implement grid search based hyperparameter tuning. So the number of neurons in a layer, number of layers to be used, the activation function to be used, all these things might be optimized based on grid search values. But all these things, the dropout, all the learning rate, all these things can be optimized by using Bayesian optimization. This is one very commonly used optimization approach, which you can try it out if you're having some already input these things, right? So which is better? So at the end of the day, you are going to have this kind of thing. But one thing we have to consider is my real life function is always going to have some noise. So it is better to calculate the noise and start our prior with the epsilon term. So this epsilon, this is just a trick, but as you see or read more data, you might be able to understand how to use this sigma n as our noise. And similarly, there are multiple expansions of multi-objective Bayesian optimization, high-dimensional Bayesian optimization, constrained Bayesian optimization. So what all process that you are doing with optimization techniques can be done with Bayesian optimization with scarce data. So these are the few tools that are available to us. Botox is one good thing that is implemented based on Bayesian PyTorch, and Scikit Optimize is very simple, and it also gives you a very user friendly or easy interface to do. It is for people who are familiar with machine learning with Python. Scikit allows you to implement all machine learning algorithms in a similar interface. Scikit allows you to do Bayesian optimization as well. So these two are few things that you can try, and Optuna also you can use for hyperparameter tuning. So these are few things that are available to us. So the big picture, first probability, then we also saw what is Gaussian process, how Gaussian process is being fit by seeing the data, how covariance matrix is extracted, how mean is extracted, and then Bayesian optimization, how smart or sequentially we sample depending on seeing the data variance and see how this can be put into good use. So as I told earlier, this Gaussian process provides the uncertainty bars. So the acquisition functions use this uncertainty to decide where to look next, and Bayesian optimization finds good solution. In most times, if your dimensionality is less than 5, with 10 to 30 evaluations, we might see a good optimization. So this is especially valuable when each experiment is expensive or time consuming. Yeah, so I am done with my presentation and I am open for questions.
Dear participants, So, do you have any questions? Please ask to Dr. Navindra, or if you have any doubt, he will clear your doubt. Let me check any questions in the chat box. If there is no questions in the chat box, sir, so we will wait a few minutes. So, dear participants, so unmute yourself, and do you have any questions? Kindly ask to Dr. Navindra. Professor, Professor, shall we conclude, sir? I think there is no questions from the participants.
Yeah, I think.
Yes, sir. Yes, sir. Yes, sir. So, thank you very much, sir, for the highly informative and insightful session. So, your valuable presentation on probabilistic optimization techniques with the scarce data, in which you have demonstrated hands-on training and different techniques that has certainly provided new perspective for all the participants. So, thank you very much, sir. So, once again, on behalf of management and organizing team, Department of Mechanical Engineering, Dr. Uh, Rangarajan, Dr. Soundla Engineering College. So, I extend my sincere thanks to Dr. R. Navin Raj, Assistant Professor, Department of Mechanical Engineering, NIT Puducherry, for sparing his valuable time with us today. So, with this, we come to the end of the session, end of the day 4, session 8 of the FDP. We look forward to the active participation of all the attendees in the upcoming sessions. Thank you all for joining us. Have a wonderful day. So, thank you all. So, thank you, Professor.
Thanks for that. Thank you all. Thank you.
Dear participants, so you may leave today's sessions. So we will meet again tomorrow morning, first session, in session 9. Thank you, dear participants. You may leave the session. Thank you.